Training video models end-to-end is extremely expensive. Videos are long, correlated and heavy. But at the same time, we already have extremely strong image models like DINO. So the natural question is, can we reuse image models for video understanding without training massive video transformers from scratch? Image models treat every frame independently. So that is going to be a problem. But videos are not just bags of images. Frames are highly correlated over time. Motion is continuous, and if you embed each frame separately, the trajectory of those embeddings over time becomes messy, curved and hard to interpret. Now here's where neuroscience gives us a hint. There's a concept called perceptual straightening. In the human brain, even though raw visual input changes in complex ways, the internal representation straightens these changes into simple, almost linear trajectories. This makes prediction easier, and prediction is fundamental to perception. So the key idea is, what if we explicitly force video frame embeddings to form a straight line in representation space? First, each video frame is passed through a frozen image encoder like DINO. No fine tuning, just take the class token from each frame. So now we have a sequence of frame embeddings, though they are not straight. Then comes a lightweight time-aware transformer. It takes these frame embeddings and temporal position information and introduces two special learnable embeddings. One token is meant to capture static information like objects, background and identity. The other captures dynamic information, meaning how things change over time. Here's the critical constraint. The model is trained so that the entire video can be reconstructed as a straight line in latent space. One endpoint corresponds to static content and the direction of the line encodes motion. Every frame lines somewhere along this line based on time. The model is explicitly trained to enforce this linear structure. And on top of that, the static and dynamic components are forced to be orthogonal, so motion does not leak into appearance. But the problem is, now how do we test if a model really understands time? So this paper introduces a brilliant diagnostic task called chiral action recognition. These are pairs of actions that are identical spatially but opposite in time. Opening versus closing a door, folding versus unfolding a cloth, or filling versus emptying a cup. These are some examples. Humans find these trivial, video models struggle, and that's where LiFT shines. Because straightened trajectories preserve direction, these opposite actions become linearly separable in the embedding space. So LiFT outperforms much larger video models on this task despite being tiny in comparison.